All right, hello everybody. Today we're going to be talking about lesson number 11. It's the final section in chapter 1, section 1.10, which is on modeling and variation. So for this lesson, we are going to be using the graphing calculator. I have typed up a lot of the commands for you on this PowerPoint. And then since we're going to be watching it together in class, I will also pull up my graphing calculator on the desktop so that you can see the commands as we work through them. But you are going to want to have a graphing calculator handy. So just as a quick introduction, and again, I had posted a copy of these notes in the class notebook. So maybe you printed them out. Maybe you want to just pull them up on your class notebook now to follow along. But the truth is you have already done modeling on your graphing calculator probably a bunch of times last year. I would imagine some of you are better at it than others. I think there were also a couple of these in the summer packet. You're basically being asked to find a particular model based on data. You could find a linear model, a quadratic model, a cubic model, all kinds of things depending on the chapter and depending on what they're asking you for. We're going to stick to the linear models for now. The process is almost the same, except when you go to choose the model type, just make sure you choose the appropriate one. So finding a linear model is also called finding the least squares regression or the line of best fit. They all mean the same thing. And then after we do a more straightforward example, we're going to be talking about direct and inverse variation. So here's the problem that we're going to work on. The number of insured commercial banks in thousands, so make sure you know that this is 9.53 thousand, etc., from 1996 to 2001 are shown below. So here's the table to begin with. We're going to kind of do a couple things to this information to make it a little bit more user-friendly. So in order to get your calculators ready for today, there are some things that you have to do. So everybody should take their graphing calculators out, and you should start by turning them on. This first bullet, you should only have to do once. Once you do it today, you should never have to do it again unless for some reason you reset your calculator. So you're going to go ahead and press the second and then the 0 key. That is going to bring up what's called the catalog. You have to scroll all the way down, quite a few options, until you get to something called diagnostic on. Make sure you choose on, not off. You have to hit enter to select it. Then you have to hit enter again to make it work. Then you should see the word done, and that means that your diagnostic is officially on. So go ahead and try it. And again, once you do this, you should never have to do it again unless you somehow restart or reset your graphing calculator. Now for the next bullet, you're going to go ahead and turn on your stat plots. And for anybody who's in AP Stat, you're probably familiar with this step. So you're going to go ahead and press the second y equals. That's going to bring up your stat plots. Probably all the plots are off, but no matter what, you want to turn plot 1 to on. And if for some reason other plots are on, you want to turn them off. You just want to have plot 1 on. Again, please make sure you note that after this activity and the homework and the quiz concludes, if you want to turn your stat plot off, go back to this same menu and then just choose to turn the plot off. And then you can go back and forth as needed whenever you're doing a stat problem. Let's say you want to enter data, not just for this example, but for future examples. You're going to press the stat key. Then you're going to select edit. You should hopefully see list 1 and list 2. If for some reason you don't, let me know and I can help you figure out how to get them back. If there is already data in your list and you want to get rid of it all at once, you're going to highlight the list name, L1 or L2, press clear, then press enter, and it should delete the whole list for you. You can also delete the values one at a time. We're going to enter all the data in a minute, but this is just giving you the background. And then if you want to see your ordered pairs once we've entered them, you're going to press the zoom button and you're going to choose zoom stat, and that will show you all your ordered pairs. Okay, so at this point, I'm probably with you in class and I'm going to pull up the graphing calculator so you can see it, but these are the steps you should refer to if ever you need to enter data into the calculator. So speaking of that data, if you take a look here, this is the same information I originally gave you with a couple of additional columns. there is a part of the problem that should have also been stated, that when they say the year 1996, they are assuming that it's years after 1990. And it really should say that, and on a test or quiz, it would say that. But because it's years after 1990, what we're gonna do is we're gonna get rid of the full year and we're gonna simplify it a little bit. So we're gonna call 1996 6 years after 1990, 7 years, 8, 9, 10, and 11 years, respectively. Whenever you're doing a problem with the years, you tend to have some kind of qualifier that tells you how to convert it to a singular digit. That's just going to make your life easier as you go to plug in the data and as you go to actually use it. So now we're actually going to go ahead and enter this data into the graphing calculator. You're going to list everything in the T column in list 1, and you're going to list all of the number of insured banks data in list 2. And again, we know that it's in thousands, so you can just leave it as 9.53, 9.14, etc. So coming up here are the steps of how you go ahead and do that. So you're going to enter the year data into list 1. You're going to enter the bank data into list 2. And again, we went over a couple of slides ago how you do that. You press the stat key, you press the edit key, and then you should go ahead and see your blank list, hopefully. So enter the year 6, 7, 8, 9, 10, 11 into L1. Enter the bank data into L2. Double check to make sure that everything matches up. We want to go ahead and see what it looks like. So you're going to press the zoom key, and then you're going to choose zoom stat. That's going to allow you to see the ordered pairs. When you look at your graph, you should see probably little rectangles or open circles, and your data should look something like this. It's not going to be perfect, but it does look pretty darn linear. And in fact, it looks like there's a negative slope if you were going to go ahead and draw a line through that data. And so drawing a line through that data is exactly what we want to do. So we're going to go ahead and find a linear model. And again, I'm telling you that it's a linear model. In future problems, it could be quadratic or cubic. They're all going to be found in this same location. So choose the correct one. In order to find the linear model, you're going to press the stat key. Then you're going to right arrow over to the word calc. You're going to see all the different options for future reference. Make sure you choose the lin reg, that means linear regression, and make sure you choose the one that is AX plus B. There are 2 different options. If you choose the one that's AX plus B, you're really choosing the one that's Y equals MX plus B, and that's exactly what we want. So when you bring up your screen, it should say L1 is the X and L2 is the Y. Again, that's what you want. Then if you hit enter a couple times or scroll down to the word calculate, when you hit enter, it should actually bring you up the information for the linear regression. So make sure that you've completed all those steps, and then I'm going to show you how to actually put it together. So when they say find the line of best fit, and again, they could say find the least squares regression line or the linear model. They all mean the same thing. So if we're using Y equals AX plus B, we're going to go ahead and plug in the values that they gave us on that screen. So for the A, you're going to go ahead and round to a couple of decimal points. So I'm going to say negative 0.283. I'm going to use T for time. If you use X, it's really not a big deal. Plus the B, the y-intercept, I'm going to say 11.14. Again, I will tell you on a test or quiz what to round to, but for now, I'm going to do 3 decimal points for the slope and 2 decimal points for the y-intercept. So this is our line of best fit. Then you also want to talk about the correlation coefficient. So the correlation coefficient tells you how good your model is. This is why we had to turn on the diagnostic. If you turned on the diagnostic, it should tell you what R is equal to. Be careful, R not R squared. So R should be equal to negative 0.992. Here's the thing about R. The closer that R is to 1 or negative 1, the better your model is. Let's say that your R was a positive 1. That means that your data has a perfectly linear positive relationship. That's the best that it could be. Let's say your R was a negative 1. That means your data has a perfectly negative linear relationship. Both of those are equally perfect. One's just positive and one's negative. So the closer your R is to positive or negative 1, the better your model. The fact that RR is negative 0.992, that is extremely close to negative 1, which means our model is really, really good. In order to see how good your model actually is, go to the y equals on your calculator. Type in this line of best fit, negative 0.283, you're going to use x plus 11.14. If you then go back to graph, it is going to show you not only those original data points, but now it's going to show you your line through those data points. And you should see that it actually looks quite good. It goes through a few of the points exactly, and the rest are very, very close. The fact that all those points are close to the line, that's because our R value is so high, which means our line is very good. Here's the final thing we want to do. We want to actually see how good our model predicts based on the original data. So you're going to pull up the table, which means you're going to press second graph. We're now going to go back to our table here. So again, 6, 7, 8, 9, 10, and 11. To see how well our model predicted, the original data is called Y. Your prediction data is usually called Y with a little hat on top. It's called literally Y hat. Or sometimes your book does Y with a little star, Y star. Either of those two notations are acceptable. The stat people are going to use the hat. The book people are going to use the star. Both of them are correct. But basically, you now want to look at your table for 6, 7, 8, etc. And you want to write down the values that your model predicts. And we want to see how close they are to the original data. The truth is they should be pretty close. So go ahead and take a minute and write down your predictions compared to the original. And again, I don't care too much about how you round it, but go ahead and find those values. I'm going to type them in. So 9.43, 9.145. If you are getting all of these same values that I have here, it means you've done everything perfectly. You've typed everything in. Just as a kind of strange thing along the way, sometimes TI-84s and TI-83s give slightly different answers for these problems. For years and years, I've tried to figure out why that is, and I still don't know. So as long as you're close, it's perfectly fine. I don't know that I'd actually have time to put one of these on a test, at least not the whole process. So that's why when you do them as practices or homeworks, again, as long as you're close, then you're good to go. So that's the entire process. How do you set up your calculator? How do you find a linear model? How do you find the R value? And what does it mean? So you're going to be asked to do that lots of times throughout the year for all kinds of models. And you can always refer back to this lesson if you have any questions. In addition to that graphing calculator stuff, there are 3 more things we're going to talk about. And it's basically the 3 different types of variation that you're going to have to know about. And again, because your quiz is open notes, these are going to be very important for you. So of course, I'd make sure you're writing them down in some way. So direct variation is the first one, and it basically has to do with linear models. Now, you guys are used to seeing y equals mx plus b. Here's the thing about direct variation. In direct variation, there is never going to be a b. You're always assuming that b is 0. So instead of y equals mx plus b, it's just y equals mx. But because it's a special case, they change it to y equals kx. So this is now going to be our simpler model whenever you see the magic words direct variation. So here are all the 3 different ways, excuse me, that in a problem, you would know that it's direct variation, which means you should be using y equals kx. Either you will see the problem say y varies directly with x, y is directly proportional to x, or they will literally tell you to use the following formula. And what is k? K is the constant of variation, also known as the constant of proportionality. Technically, it's the slope, but again, because we're using this special model, it's basically telling you exactly how the two things are varying. So it's the constant of variation, or again, the constant of proportionality. So keeping that in mind, let's look at problem 1 here. The simple interest on an investment is directly proportional to the amount of the investment. So whenever you see the word directly proportional, or you see any of those 3 buzzwords there, you know that this is a direct variation situation, which means you know that it's y equals kx. You then want to rewrite the problem using variable letters that make sense. So the simple interest is directly proportional to the amount of the investment. So I'm going to say that the interest is directly proportional to the amount of the investment. So investments are usually called the principals. So we're going to call that P. So again, start by realizing that this is direct variation because of the buzzword. Use appropriate variables, I for interest and P for principal, that's the investment. Once you have the equation, you can now do lots of stuff with it. And it says by investing $2,500 in a certain bond issue, you obtain an interest payment of $187.50 at the end of 1 year. Find a model that gives the interest for this bond at the end of 1 year in terms of the amount invested. So basically, all you're trying to do here is use the value that they're giving you, the ordered pair, and you're going to go ahead and solve for k, and then you're going to have the magic equation that you can use for anything. So they're telling you that if you invest $2,500, you're going to wind up with $187.50. So $187.50 is the interest. We're looking for the k that made that happen. And we're going to go ahead and plug in for 2,500 for P. In order to solve for K, you're going to go ahead and divide both sides by 2,500. So you're going to do 187.50 divided by 2,500. If you do 187.50 divided by 2,500, you're going to get a K value of 0.075. Which means that the formula you can now use for anything having to do with this problem is I equals 0.075p. So that is always the relationship. Because they are directly proportional or direct variation, whatever the principal is, if you multiply it by 0.075, you're always going to get the corresponding interest rate. So here's how you do the problems. Discover what the original equation is, replace the appropriate variables, solve for the missing value, and then you have a formula that can be used at any time. Let's say that it is not direct variation, or at least not just direct variation. Here's the second type. You can have direct variation as an nth power. So that still means that it's direct variation, but instead of just being linear, it could be anything. So again, here are the buzzwords: varies directly as the nth power, directly proportional to the nth power, and the magic equation that you're always going to use is y equals k times x to the n. So again, the main difference between this formula and the previous formula is now you're allowed to have an exponent. So let's take a look here. Neglecting air resistance, the distance s an object falls varies directly as the square of the duration t of the fall. If it falls 144 feet in 3 seconds, find an equation that relates s and t. So when you see varies directly as the square, that's how you know that varies directly is y equals kx. And then the fact that it's a square is how you know that it's not going to be linear. Then make it specific. You're trying to talk about distance and time. So the distance varies directly with the square of the time. So that is now your equation using the appropriate variables. They tell you that an object falls 144 feet. That's a distance. 3 seconds, that's 9. In order to solve for k, you're going to do 144 divided by 9. 144 divided by 9 is 16. So that's how you know that you're going to get S equals 16t squared. And that should actually look familiar. That 16t squared, we'll talk much more about that in the next chapter, but that's ultimately what you're looking for. So far we've seen direct variation. We've seen direct variation as a power. And then the last one is inverse variation. So inverse variation is the third option. And here are the buzzwords: varies inversely or inversely proportional. And here's the magic equation: y equals k over x. Indirect variation, as x got bigger, y got bigger. Inverse variation means as x gets bigger, y gets smaller. So kind of common sense. Please make sure that you are aware that there are some problems that ask you to combine direct and inverse variation, and you're going to see some of those on the homework tonight. So basically, you have to read the problem very carefully and then translate the words exactly into either some kind of direct variation or some kind of inverse variation. So plenty of examples that ask you to combine all the three different types. So you'll get practice on that tonight in the homework. One last problem: a company has found that the demand for its product varies inversely with the price of the product, and that should make sense. The more expensive something is, the fewer people that want it. The cheaper it is, the more people that want it. So when you see that relationship, that's how you know that it's y equals k over x. Then they want you to specifically use variables. So they're talking about the price and they're talking about the demand. So the demand equals the k over the price, which we'll call P. When the price is $275, the demand is 600. So 600 is equal to k over 275. In order to find k, you're going to cross multiply, and turns out that k is 1650. That means that my equation is D equals 1650 over P. For all the previous problems, that was it, but then they want you to go one step further, find the demand when the price is $3.25. So all that means is you're going to go ahead and plug in the price of $3.25. And your final answer: when you price something at $3.25, approximately 508 people, decide that they want to buy whatever it is. And again, obviously it was a decimal, so rounding 507 point whatever to 500 people would be more than sufficient. So here's homework 11. Homework 11 is all about different kinds of variation. I think there's maybe one or two that have something to do with the graphing calculator, and then the rest have to do with all the different kinds of variation. So this is the final lesson of chapter 1, coming up on another assessment soon. So thanks guys for tuning in, and we will catch you next